Yeah, I hope you can. Hold on a second.
Okay,
here.
let me wait.
Well, let me just do the quick introduction. So we're very happy to have part 2 of our talk on the Axion strings in the CMB from Junwu Huang, who's got his PhD at Stanford, and he is now a junior faculty, first I guess postdoc, and now junior faculty staff, I don't know what it's called, at Perimeter Institute. So welcome and take it away.
Thank you. Yes, so I was actually invited to give a talk almost exactly the same time last year. Dario invited me and I couldn't come. Last time I was planning to talk about part 1, but now since Anson talked about the part 1, I will give you the part 2 of the talk. So, so first, like I will start with something that is more related to what he said last week. And actually, like I will start with a short review, but I think it's the same audience from last week. So, so this will be very fast. So what Anson told you last week is that we can look for axion strings through measurement of CMB polarization correlation function. Like, can you see me see my mouse actually?
Yes.
Yes.
Okay. Yeah. So through like the map like this, which can be generated when you imprint the axion string on the CMB photons. And the effect we are looking at is a topological phase or near topological phase that can be generated by when a photon goes around the axion string. In reality, we are measuring photons which are coming from very, very far away. And as a result, like there were 2 half circles instead of a full circle. So through these and these axion strings leave a distinct polarization pattern in the CMB. Which we can search for through 2-point functions of 2-point function correlation, 2-point correlation functions of this polarization rotation field phi, which experimentally means there is a EB-EB correlation we can look for in the CMB pattern. We can compute both from analytical computation and also like a numerical simulation, these 2-point functions and which agree very well with one another, and for which we can search for with Planck and also future detectors. And this leads us to this last figure here, where we can place constraint or maybe look for these signal, which scales always with Xi, which is the number of the string per Hubble patch times this anomaly coefficient A, the squared. Okay, so and that is why for all of these 2-point function measurement, we are looking at these constraints or like a reach, which are these 60-degree lines in this figure. Okay, so just to remind you again, the interesting targets that we want to get are this solid red line and the dashed red line, which correspond to UV particles, which can have charge that is integer in terms of electric charge, or integer in terms of quark charge, or 1/3 in terms of the electron charge, which gives you 1/9. So, and you can see that with 2-point function, we can potentially get most of the regions that are interesting with, for example, Simon's observatory, apart from the region where like Xi is very small, which means like there are a very small number of strings in the universe.
Sorry, I know you just said this probably, but sorry, I just missed it. What is Xi again, or Xi? What is it?
Xi is the number of string per Hubble patch.
Oh, right, okay.
Or like the total length of the string, like in a Hubble patch over the Hubble length.
Thanks.
Yeah. So yeah, so like the 2-point function is very good when you go for like a Xi that is large, and for Xi that is small, you need some new method, which will be the first part of what I will be telling you about today. Yeah. So following string chart's suggestion, I will stop here, and if people have questions about what I said last week, I can take some questions.
other was my suggestion? I don't remember.
That was what you told me like during the pandemic. Yes. VSM pandemic. But anyway, that's why I have this slide. Okay. So if no further question, like I will be telling you today something different. So all of today's observable that we will talk about are observables in position space or in angular space. So these are like real features in the sky instead of the measurements that Anson was talking about last week, which are all like in terms of L space or like a Fourier space. So the first thing like I will be telling you more about is, and as I mentioned a little bit, is like this edge detection method, which is still like a measurement that we can do with the CMB. And then like we'll move on to something that is quite different, which we call a plasma collide. So as you can see from the figure, the signals or like the features that we are seeing are real position space features. For example, you can track the string from this point here, for example, all the way here. And these are really long strings. There are really long strings, which basically span the whole size of the universe. And what it tells us is that potentially like it is better to look for these space, like really position space features in position space instead of checking some 2-point function.
Sorry, can I ask a question? So does this sort of a picture rely on these strings being very large and living for a long time? Can you say something about that? I mean, how much is known about
yeah.
that?
So like if axion mass is 0, then like these strings will live forever, okay? And they will like always connect with one another, forming loops. Some of the energy is lost, such that the string always stay in the scaling solution where there is one string with a curvature radius that is of order the size of the universe at the same at one time. Okay, and those are those long strings which are still present today, right? These are strings that's in the universe with us that we are looking for with these angular space variables.
Yeah, I guess I was thinking of string interactions, but I guess if they're sort of order 1 to thousands per Hubble patch, those are rare enough that the strings pretty much survive for order a Hubble time or something like that. Typically,
yeah.
Is that right?
They interact with one another like pretty much every Hubble time. Yes.
Okay. Okay. Thanks.
Okay. Good. So how do we do that? So here, like we have a zoom version of the figure that I showed you before. And these numbers are basically in degrees. So we are looking at a patch which is a few degree in times a few degree like in size. So here, like you can see, there is a clear edge which comes from a very long string that is existing in the universe, which has a curvature radius that is comparable to the Hubble today. So these strings, like with such a large curvature radius, will be straight on these smaller angular scales. And they will be straight on like angular scales of 10 degrees or even like a few 100 degrees. So the experiments we have since maybe like 10, 20 years ago are like these ACT experiment or SPT, which are ground-based detectors, which has very good good angular resolution, and also future like experiments like Simon's Observatory, which will improve on that. So this measurement has a very deep measurement of an area of view, which is of order 100 degrees squared, so a little bit bigger than the size that I'm showing you here, whereas angular resolution that is order arc minute. So for each string which is going around, like in the universe like this, you are really looking at an edge that is straight and consistently for like thousands of pixels. So and these are very, very sharp features which we can look for in position space. So this is what we set out to do somewhat recently with 2 people at Berkeley. They are real cosmologists, so they are doing most of the work right now. So And with this analysis, we are hoping that we can achieve 0.1 degree sensitivity on this polarization angle. So here is a test that we did, which I'm showing you in this figure here. So on the left-hand side is the truth information. So the white is where the string is, and the red and blue color correspond to polarization rotation in one direction or the other. So here we basically place a bunch of string in parallel with one another, which gives you this pattern. So the second plot is what happens when you apply this pattern on a noisy CMB map. And unless you are really, really good at seeing features from a noisy map, you see nothing, which is why I didn't even show you the plot to start with. But if we look in on top of this noisy Poisson map, in the second picture, for features that are basically localized regions where polarization is going one way continuously in a large enough region, then we can recover the third plot. And here, we haven't even used the fact that these strings are straight features in position space. And we can recover a plot which is very similar to the first one. And these features that we see can be resolved by eye. And it goes to polarization angle sensitivity that is of order 0.1 degree. So this is on some mock data that we simulated, and we are hoping that we can develop this method and apply it on real data to find if there are string-like features in the position space in polarization data. Okay. So what does this 0.1 degree mean? So if we can get this sensitivity of 0.1 degree polarization rotation from the polarization map, then we can improve this edge detection method to basically the dashed line here. Okay, and you can see with existing data, and you can see this method is very good for small c, because the edge only depends on the anomaly coefficient. It doesn't really depend on how many strings I have in the universe, and so it will allow us to cut in a piece of the parameter space that is hard to get with the two-pole functions. Okay.
So here you're going up to xi equals 10 or up to around xi equals.
Yeah, so you see this is solid
3.
and this part is dashed. And that's what I will be telling you later here, okay? So if I have c equal to 1, right, in a field of view, which is of order 10 degrees squared, Hosing squared, you are really seeing a very small number of strings. You are seeing a very straight feature, and it is easy to resolve with this method, okay? But now, if you increase C more and more, there are more and more strings which are on top of one another, in this in your field of view, and the sharp features start to blur. And once you get to a C to equals 100, you are reaching the large C limit, where basically all the strings are on top of each other, and the field of view would have a polarization pattern that is roughly Gaussian, right? So the large C limit should give me the Gaussian, give me back a Gaussian result, and the Gaussian estimator, the two-point function that we designed to look for this effect, should be optimal. Okay, so so that's another way to see the complementarity, where the edge detection start to fail, which are these large C numbers. We have the two-point function, which is giving us a good result, and we are trying to figure out exactly where this cutoff between where edge detection is better and the region where the two-point function is better. It should lie somewhere around C equal to 10. But we need to look at real data to be sure. Yes. So this is a work in progress. Okay. All right. So let me say a little bit about this tentative hint that I think many of you might have heard about. So which motivate us to apply the method we are developing to something else. So recently, like Mainami and Komatsu reported result of from like a Planck polarization measurement, a uniform polarization rotation of 0.35 degree, which is a number which is very close to the fine structure constant alpha ENM. Okay, so such a rotation, if you like really interpret it as a uniform rotation everywhere, is in slight tension with the data from like X 2020. And so like there is some debate which is going on between them. So what we were thinking is that could this signal be coming from the strings? And the way like it can come from the strings is the cosmic variance. So if you look at this plot here, where we have like a lot of small loops, you have like small loops everywhere, and they like overlap with one another. So their effects start to cancel out for these small loops. On average, you do not expect very much from the small loops. However, when you think about the biggest loop, like in the universe, that is a loop which is not canceled by another loop, which gives exactly the opposite result. And as a result, we can potentially be seeing this 1-point function which comes from the last loop in the universe, the loop that is in our universe, which is of order the size of the universe. And as a result, we should be looking at the polarization map. And if such a string is there, I will be seeing like a patchwise uniform rotation. So inside, like there will be a polarization rotation, which is one angle, and outside is another angle. And on average, you can get like a polarization rotation, which averages to somewhere close to alpha ENM. So we think it's a possibility that we are seeing like, well, like they are seeing like cosmic variance coming from strings. And we are doing some investigation with the method that we are developing to look at this scenario.
That's when you say it's in slight tension with ACT 2020. What does ACT see? They don't see polarization, or what do you mean?
They do not see like a EB correlation in their patch of the sky.
Okay, you say
they put a constraint on beta, which is smaller than the one that is reported by Komatsu.
Yeah. They just saw a small patch of the sky where the uniform polarization was from the whole sky.
Yeah. The uniform rotation is one like is basically Planck, which is all sky. Well, ACT is a ground-based detector, which only have like a deep measurement. It has a better like a resolution measurement of a smaller patch of the sky.
But isn't it easier? Usually by fluctuation, easier to see some polarization if you have a smaller patch. But when you have a big patch, they average out.
But like the patch that you are seeing in ACT could be like a patch which is not rotating, right?
Okay.
And that is the possibility that we are testing with the method like applied to something like a Planck data. Okay, so that's all I want to say about edge detection. Any questions? Okay, so let me move on. So in the second part, well, so first the intermission. I think like most of you have heard that our receivable is no more, and we'll be talking about some signal which like our receivable will be like a grade to look for. But like there are like some other detectors that we'll be looking at. So so since like the second part will be very different from the first part, it's time that you can clear your mind, and now we dive into the second part. Okay, so
what is Arecibo? I don't know.
Oh, Arecibo is like a dish, like a radio detector. So this is the detector.
I can see that, but is it like the largest one, or what?
Yeah, it was the largest one. Like now there is another detector called FAST, like in China, which is bigger, like which is 500 meters, but like the sensitivity is comparable. Yeah, Arecibo is something that's in Puerto Rico, which got destroyed in the hurricane, I think.
Oh, okay.
You discovered the binary pulsar.
Yeah,
Oh,
yeah,
okay.
yeah.
James Bond films.
Yeah, it's also in the James Bond
Radio
film.
telescope in the world.
Yes.
Right.
Anyway, the detector is no more, so yeah. But like, okay, anyway. So in the second part, we'll switch to a different topic. So from what Anson was telling you and like also what I was telling you earlier, we are talking about how the axion string can affect the photon propagation, right? How the photon can accumulate phase randoms going through this string network. So in this part, we'll be asking the opposite question, which is how does the axion string affect, like how does the photon affect the axion strings? And in particular, we'll be looking at how like a coherent electromagnetic field in the universe, for example, a galaxy magnetic field is going to affect like the dynamics of the axion strings. So that's the topic. And for that, I will need to introduce you a little bit more about axion strings. So so here like is something that is well known, which is the PQ Lagrangian, where I have a complex scalar field coupled to some PQ quarks, which is charged on a ENM, which gives rise to this AFF Tubular coupling. Okay, so the complex field also have a potential, and which allows it to develop a field profile like in most of the space, which is equal to where like the real component is equal to the F, which is the axion decay constant. And then like there's a pseudo-Gaussian boson or Gaussian boson, which is the axion, which rotate, which is the angular field. So a string solution is a solution where like at the core of the string, this complex scalar field phi has a zero VAV. And you can see that from this Lagrangian that when I have like capital phi equals to 0, these fermions, which are charged under this phi, are well, which is coupled to this scalar phi, will get a zero mass, and these fermions will only be massless on the string, and that's how you see that you will have like this localized zero mode, which live on the string. So I can show you like in more detail later, but right now, like you have to believe me that these fermions which live on the string are chiral, meaning like they in this 1+1D like effective field theory on the string, they are massless mode which only moves in one direction. Okay, for example, if you have a vortex, like so you will have this fermion which has a wave function which depends on x minus t. So if like I have a charge plus fermion like on the string, then it will move to the right, and I will call that like a current bigger than 0. Well, like if I have like a negative charge particles which are living on the string, they will still move on to the right, and in that case, I will have a current flowing to the left, which I will call like a current less than 0. So these string localized fermions are massless, which means they propagate without impedance, and which is why some people say that the axion string core is a superconductor, and in particular it is a chiral superconductor, where the charged particles only move in a single direction on this 1+1D theory. Okay. So
can I ask a question? In what sense is the superconductor?
Huh?
In what sense is a superconductor?
Because like there's no impedance on the string, so like if you set up a current, it will flow forever.
Okay, there's no resistance. Okay.
There's no resistance. Yes, on the string itself, on the core. Yeah.
Okay, sure.
So that's a very short like part of about like some string basics. So now we want to understand how the photon like or electromagnetic field like affect like these superconducting axion string. But first, let's look at a simpler system, which is how does the electromagnetic field affect like a real superconductor, right? So let's say like I put a superconducting loop in a magnetic field, and I'm moving one of the edge, which is this red line here. Okay, so when I'm moving this red line inside B field, what you'll get is a current which gets generated, and such that it compensates for the flux the like the fact that you want to like move the wire to change the total flux that is going through the superconducting loop. So you can compute like the value of the current this way, and you will see that the current is flowing in the direction which is given to you by basically the Lenz's law. Right? So for a real superconductor, a bulky superconductor, what you know is that the flux that is going through like a superconducting loop is always a constant. Like no matter how you change the shape of the superconductor wire. And that is coming from the fact that the charge carriers have zero velocity in the bulk of the superconductor. Here, like I make this wire like a little bit thicker, and here so that there's something we can call bulk, which are basically regions of inside the superconductor, which are very far from the edge, the surface, and this distance is bigger than the penetration depth of the photon. Okay, so when we have like this bulky superconductor, the flux inside the superconducting ring is always quantized, and it always remains a constant. Right? So back in the 60s, people try to understand a little bit more about the system. And in particular, there's a very nice effect or a very nice experiment by Little and Parks, where what they did is they take the like a superconductor and make it very, very thin, okay? So thin that the thickness is comparable to the penetration depth of the photon. So now like you cannot talk about like the bulk of the superconductor anymore. And as a result, flux is not necessarily quantized, and it is also not necessarily conserved. Only like a fluxoid, which is the like the terminology that is used, is quantized, and magnetic flux can actually go through this very thin superconductor. Okay, so as a result, the amount of current that you need to generate on the string to compensate for that flux change, the intended flux change is smaller, and as a result, like you will see a smaller current on the string, which is suppressed basically by how non-bulky your superconductor looks. Okay. So this is exactly what happens for superconducting string. So in particular, like for Witten superconducting string, and this is analysis that he did in 1985. So what Witten studied is a cosmic superconducting string, not an axion string because there's no, like in his case, there's no anomaly. So just a normal superconducting string, which is moving through electromagnetic field. What he discovered is that the scattering rate of the string within magnetic field is almost geometrical. By almost geometrical, I mean like the cross section is proportional to the wavelength of the photon, 2 pi over omega here, times the length of the string. But it is not totally geometrical like a real bulky superconductor, because this cross section is suppressed by some e squared over 8 pi cubed, or alpha squared, times this eta factor, which accounts for the IR divergence of the string energy. Okay, so basically, like what he showed is that his superconducting string is not like a real bulky superconductor, and you can understand it because like this superconducting string has a thickness of order like 1 over f, which is really, really tiny even compared to any other scale like in the theory. So this imperfect geometric cross section is one of the main features of these superconducting strings. And
what's the connection between this and the imperfect thing? I mean, I don't understand. I mean, why is this? I don't understand is there supposed to be a relation between this and the thin superconductor?
Yeah. Right. So like what the Little Parks effect shows you is like if I have a superconductor with no bulk, okay, meaning like the penetration length of the photon is larger than the thickness of the superconductor, flux can actually go through.
Right. So
and the superconducting string is one
this,
example of that.
right. So I can think of this interaction that Witten calculated is some residual interaction between the superconductor and the okay.
Yeah. But that's how you see like why flux can go through, basically because his superconducting string is super thin.
So the field phi is in the string is charged under E and M or no?
There are like a charge, like a charge carriers on the string, which is charged under E and M.
Yeah, it doesn't carry electric charge, right? Because electric charge is unbroken even in the vacuum. But the fermion on the string is carrying electric charge. Is that the point?
So for Witten string, there's no like anomaly, and as a result, there's no charge. So there's only a current.
So what is the basic interaction that's causing this? The photon is coupling to what is charged under E and M here? I'm sorry, I'm just being very slow.
So in his case, like you can think of like there are like charged particles which can move in basically both directions on the string, which are massless.
So that was my question. The chiral fermion on the string is electrically charged?
Yeah.
Okay, so I can think of this as an interaction between the photon and that.
Yeah.
Okay. All right.
Yeah, I will say like a bit more like in the axion string case where like it's easier to understand. For like a Witten, like he can have like a boson and fermion charge carriers, and the story is a little bit different. But yeah, like it will get clear like when I go to the axion string case.
Okay.
Okay. So now let's try to address the question, which is what does the photon do to the axion string? Okay. So for that, I will need to tell you even a little bit more about the axion string and axion E and M. So here, like again, like just remind you, like I'm talking about axion string, where like the angular direction around the axion string is a field, which is the axion field. And around the string everywhere, like there is a gradient of an axion field, right? The gradient around the axion string is basically 1 over r. Okay, so and then like on top of that, like if you remember, like from Wilczek 87, like if you have axion field with some gradient in electromagnetic field, this axion profile is going to carry charge inside the electromagnetic field. It's going to source some additional like electric field and magnetic field, which and the density is proportional to the gradient of the axion field times the magnetic field, and there's a current which is a gradient of axion field across the electric field. So these charge density and current density is known as the Goldstone-Wilczek current, and we'll be looking at those in the next slide. Okay. So this is what you see here. So now imagine like this red line instead of a real superconductor, an axion string. So this axion string is going to come with its own axion profile, which has some gradient of the axion, and as it is moving through the magnetic field, this charge, which is stored in the gradient of axion field, is going to change. And if you do the math, what you will see is that the charge that is stored in the axion field around like this axion string is basically proportional to the total magnetic flux which is threading through this axion string. Okay. So now if I take my axion string and move a little bit, and since we know that these string-like objects are imperfect superconductors, this flux can change, and as a result, the total charge that is stored in the axion profile is going to change as well. Okay, but of course we know like the electric charge has to be conserved in the system, right? So what is happening? Well, what is happening is that there will be charge which are popping up like on the string itself. So the other equation that we can use from Maxwell is the fact that there is going to be a curly electric field, which is going around the loop when you change the magnetic flux, which is threading through the loop, right? So there is going to be a potential. So what this potential electric field on the string does is it's going to pop out like a charged particles. And since like the charged particles we have on the axion string is massless, we can basically produce them like however much we want through what like the analog of Schwinger pair production, right? Which is proportional to the electric field in this 1+1D theory. And these charge which are popped out is going to cancel, which is going to be equal to the amount of charge that is lost in the axion profile. And the other way that you see like this has to happen is, as I was telling you, when this superconductor is moving through the magnetic field, is going to develop a current. And as I was saying earlier, when you have a current which is on the axion string, because the fermions on the axion string is chiral, that has automatically means there is a charge that has to come with the current. And it is the same charge that are popped out from the vacuum, and it is exactly the same charge as what you expect from the loss of charge in the gradient of axion field coupled to the magnetic field. So that's how you understand charge conservation. And we can even find the current that is moving the charge from the axion gradient to the string core. And that is basically this term here, where like the axion gradient is the theta direction around the string. The electric field is developed when you change the magnetic flux, and that sends some charge to the string core from the axion field. So if we do like everything like carefully with order 1 numbers taken into account, we can see that the charge is always conserved in the system, and the effect, as we know it, is called anomaly inflow. Okay. So what do we learn from? Of course, I was giving you like this concept of anomaly inflow in terms of very simple like axion charges, but like you can compute it more rigorously like in many other ways, which I won't have time to cover. But like the effect that I have been mentioning is telling you a few things. The first thing is that there will be in addition to current deposition on the string, which is also the case like in the case of the Witten string. For axion string, because of the anomaly and because of the chiral fermion which is flowing on the string, there's also always going to be a charge deposition. And that charge deposition is proportional to the total magnetic flux, which is changed when the axion string is moving in the sky. So we can compute how big this charge is. So for each galaxy crossing, and here like I'm taking some like a magnetic field, which is microgauss or 10 microgauss, which is coherent over a length scale of order kiloparsec. You will be finding this charge, which are deposited on the axion string core to be of order 10 to the 45. And if you compute the charge density on the string, which is this lambda parameter here, it can be as large as 10 to the 8 or 10 to the 9 GeV. So this this is a really, really densely charged wire. If you only look at the axion string core, that is spreading over kiloparsec distances, which develop like a very large coherent electric field that potentially you can look for. Okay?
Sorry, can I ask a question?
Yeah.
I mean, I didn't follow all the details, but my understanding is that there's this, right? This effect is coming from, as you said, there are these gradients of the axion field, you know, near the string, and those carry charge, right? When in the magnetic field. But now, just in general, right? If somebody comes up to me and tells me, hey, there's some excess charge over here in this part of the universe, then I think, well, that what will happen is that it will get neutralized, right? Very, very quickly, very efficiently. Because
exactly.
electrons are going to flow around. They're going to do what they need to do. So my question is, why is this effect not canceled by that kind of thing? Or why isn't that, an important part of this?
That's exactly what will happen like after this slide, okay?
Okay, it hasn't happened on this slide yet. All right.
Yes. Right.
All right.
Okay. So, but before we go there, let me give you a short summary. So we are looking at like axion strings, which is a type of superconducting string, which is also like loosely related to superconducting wire. So what is special about these axion string is the charge carriers are chiral fermions on the string. They carry a current and a charge, and normally like you will have the current, which is larger or equal to the charge, which of order the fine structure constant times the total magnetic flux, which has changed when I'm moving the string around. Okay, so this is all about the string core. And as Marcus was saying, when you have like something that is really highly charged in the universe, electrons is going to move around and it will be canceled. Okay, and that's exactly what happens. So so here, like I'm showing you an axion string, which is carrying a current here, and it is carrying like a positive charge. Okay, lambda q is larger than 0. So itself like has a very small core, which is 1 over Fa. But once like this charge is slowly developing, the negative charges in the surroundings will be attracted towards it, and the positive charge particles will be expelled away. Right. So this is what is shown by these negative charge particles here. So the negative charge particles will be accelerated by the electric field, and as it is moving towards the string, it's also going to feel the magnetic field, so it is going to move along the string as well, like in the direction which is the same as the positive charge is moving on the string core. Right? So what this does is that though we work very, very hard to set up a system where like I have a string core which carries both charge and current, the universe automatically does like what we exactly the opposite of what we wanted to do. It sends like the negative charge to cancel exactly the charge over density that you develop at the string. Okay. So, but this is not too bad because of what I will be showing you later. Okay. So for this part, I would like you to think about the system zoomed out. Okay. So here, let me again start with a normal superconducting loop or superconducting string. So the red circle is a superconducting loop. And if I really like see it from very, very far away and ask like what is the effective description of this loop, it's basically a circuit, right? It's a circuit with a capacitance and inductance. And the capacitance and the inductance are both of order the length of the string. And as a result, if you set up a superconducting loop or superconducting string, and you put some charge like a current over densities in different places of this loop, what you'll get is basically the exact response of a superconductor. It will be a LC circuit with zero resistance. It will oscillate forever, right? And that's what happens if you are thinking about a Witten string or like a superconducting loop. The axion string is a little bit different, okay? So on the axion string, though the charges that is living on the axion string core, it is like a massless and it is superconducting. The core is superconducting, but like the charge particles that you're attracting from the medium to form like a dense cloud or like a plasma of negative charge particles outside, these particles, of course, they dissipate, right? So what you realize is that not only is the axion string not really carrying charge in the universe, it is not even like very well superconducting, because the charge cloud outside has a resistance and it dissipates. And as a result, to describe the behavior of charge over densities on axion string, which you are looking at is an RLC circuit, right? So it is a dissipative system, and the charge over densities will like eventually like spread out. It will become uniformly charged with maybe like a positive or negative charge, but there will not be like a persistent like a charge over densities. And the uniform charge configuration, of course, is the lowest energy configuration, which is what it will relax to. Okay. So what I tell you from the very zoom out picture is the following. The string core is a very good superconductor, but the plasma cloud is not. So the whole thing is not a very good superconductor. The charge over densities will spread out, and during this process, energies will be released by the system. And that is great, because unlike a Witten string where the thing just go on forever and then nothing is really released by the system until you like have to break the EFT, for the Axion string, it is always dissipating. And when you have a dissipation, it means there is a signal that you can look for. Okay? And this picture is going to show you the signal. So here, what I'm showing you, so first, like ignore the red lines here and just look at the black. So here, what I'm showing you with these black lines are the magnetic field of a galaxy. And what we have here are two galaxies which are spaced a little bit apart. Okay, so these two galaxies has magnetic field lines which wind in different directions. And as a result, when the axion string passes through, one of them is going to charge the string with positive charge, and the other one is going to charge it with negative charge on the string. So of course, these two charge sections is not going to be charged because the plasma is going to quickly neutralize that. And now you have like a two blob of plasma which is moving along the string. The blobs will be traveling in the same direction, but at the same time, like they are going to spread out. So as long as my two galaxies now very far apart, they will collide at some point before the charge densities is totally smoothed out over the axion string. And these collisions are what we can look for. So so these collisions can not only happen like in between galaxies, which is what I'm showing you here with the two black circles, but like it can also happen like in the same galaxy because all the galaxy magnetic field is dipole field, and as a result, there are regions where like you are crossing the magnetic field one way, and there are other regions where the axion string is crossing the magnetic field in the opposite direction. So positive and negative charge particles will be developing on the string, even if it is going through like the same galaxy, and these charge over densities will want to neutralize. And the plasmas, when they collide with one another, is going to give you the dissipation, and it's going to be the signal that you're looking for. So how often do this happen? Okay, so we are looking at, so for that, we take parameters like c equals 10, and with a normal coefficient, let's say, equal to 1.
Sorry, can I ask to make sure I'm understanding this? I mean, this
Yeah.
this collision depends on the fact that the resistance or the dissipation in the string is not too large. I mean, I could imagine that if that was very large, then these excitations would dissipate away before they ever collided. Am I thinking about this wrong?
So like if the dissipation, like, I mean, like the resistance can at most be like 1 over L, right? Because like the eventual thing is like it is going to be uniform.
Oh, right, okay.
So like the wave packets are basically like two things which are both spreading and they want to catch one another. And as long as you set up them to be like close to each other, they will eventually collide before like the overdensity has totally spread out.
Okay, so it's something like the typical number of times that the typical distance that one of these excitations can travel is of order the length of the string itself. Is that correct?
The typical like length is the length of the string, but like if you set up a system where like there are close by galaxies,
Sure.
Then the
sure.
amount of time that they travel is basically the distance between them.
Yeah. No, I understand. But I'm just saying that's sort of how big the dissipation is. And it basically lets you go around the string sort of once or something, very roughly.
Yeah.
Okay, thanks.
Okay, good. So like these are just some numbers that we computed. Like it's easy to estimate. There are ordered like 100 of these galaxy string crossing that you have like in the universe.
Sorry.
And out of these 100 like crossings, most of them is going to be happening in a galaxy cluster where there are multiple galaxies, which is charging the string at the same time, and which like and these crossings like of inside a galaxy cluster will result like in collisions. And if
sorry, can I ask again? I'm sorry. I'm sorry to keep interrupting, but I'm trying to make sure I follow. So,
sure.
So my understanding of when you said it was superconducting and then you said it wasn't superconducting, the way naively I would understand this is that, okay, the chiral zero mode is made out of some particle which away from the string is very massive. It might have some mass of order F axion or something.
Yeah.
Right? But in our world, we have these electrons. We have these things called electrons.
Yeah.
And there's lots of electrons around, right? And the dissipation is coming from the fact that the electrons are able to cancel this field. If we didn't have electrons, if we just had these ultra heavy guys, then there would not be this resistance. Am I thinking? Is that correct?
That's correct.
Okay.
You need light particles to dissipate. Yeah.
Right. Okay. Good. So but then my question again, coming back to my earlier question, is so why is it that so there is a kind of the fact that you're telling me that the resistance is very roughly going like the length of the string, is that just a pure coincidence? Because that has to do with properties of the electron, right? The fact that I have plenty of electrons around that can cancel this and so on.
Yeah, so that basically assumes like dissipation is like efficient. So like if it is like if the local like dynamics of the electron is super efficient, then it can go around once. Mm-hmm. If it is not very efficient, then it might go around like more than that.
How come it can't be more efficient than that? Is there a simple way to see why it couldn't just immediately damp things before it has a chance to go around?
Well, like let's say like you only have one charge over density, right, which is set up at a location. For it to like spread to uniform all across the string, it will at least take like all the Hubble time, right? Because nothing is really traveling faster than light.
The time scale to uniformize the whole string, and so sort of by causality, it has to be okay. And these things travel at the speed of light. Okay, I think I got it. Sorry, thanks. Sorry for interrupting.
No problem. Like I should have mentioned more. So so coming back to this, we are talking about these collisions of like this positive and negative charge plasmas, which can happen like inside a galaxy cluster or like a little bit, or even inside a galaxy. So the amount of collisions is order 10 or like even a little bit more, like depending on like what you assume about the galaxy field configurations. So then we can compute like what's the power. The power is basically the charge density on the string squared, which can go up to like 10 to the 40 erg per second, or otherwise known as the 7 order magnitude brighter than the solar luminosity. And such a collision can happen basically for as long as this charge over density is like the charge over density is basically has a length which is of order like the size of the galaxy, and as a result, like this collisions is going to keep happening for at least like tens of thousands of years, and for us, like for people like time scales, this is basically infinite. Okay. So these collisions are very, very bright, but they also happen like really, really far away, right? Because there are only like a few strings in the whole universe. And like the average distance between us and the string is of order the Hubble scale. So they get so the power gets penalized by like the 1 over r squared expansion of a lot. Okay.
But
So
they, oh, sorry, but they would also be coming from places where there are two nearby galaxies, right? And a galaxy
yeah,
is a lot brighter than 10 to the 7 suns, no?
yes. So that's what I will tell you now. Yes.
Right.
So yeah, so like you can do different type of searches. There are like two ways you can look for these things. One is a survey, which is basically a blind search. You just look for like regions where like there are bright like collisions. And like in the case of like this type B collision, which is a collision resulting like you're going through like two nearby galaxy, these collisions will happen outside the galaxy, and as a result, like you can distinguish it from background. The ones where like it is inside the galaxy, you pretty much cannot see like with blind search. So there is also a possibility where we can do a dedicated search, and that requires us to do some cross correlation. And the thing that makes that possible is that light always travels at the speed of light. So so like if we look for like strings in the CMB map, the CMB photons will be coming across this string exactly at the same time when this collision is like the photon which is coming from this collision leaves the string propagating towards us, right? So so in principle, if we know the map of the axion strings from CMB measurement, we know exactly where like these collisions will be happening if we cross correlate this string network with the galaxy surveys that we have. So if we do that, then there like will be like a few spots where we think like these collisions could be happening, and we can point our detectors to look for them. So and that is the prospect. So here, like we're assuming like 10 to the minus 2 or 10 to the minus 3 of the total energy is emitted in radio frequencies. And what we will find is that the current sensitivity of various detectors, so CHIME is a detector that can only do survey, and SKA and FAST will allow us to like point at a particular galaxy to see like if there's some of these signals coming out up, which is not inside the galaxy. And you can see like these searches that we can do is somewhat complementary to the searches that we can do with the CMB. And they pretty much give us the same type of sensitivity over this very same parameter space that we are targeting. And that's all I want to say about this part. And thank you.
Okay, well, thanks very much. Let's unmute and thank Junwu.
Maybe I missed it. Could you just explain again, how do you do this dedicated search? How do you cross-relate these two effects?
Yeah, so that requires you to like already see the string with CMB.
When you say you see the string, you see exactly where the string is, or?
Yeah, with the edge detection method, right? We can basically know exactly where the string is at, and from its length, we know exactly like how far it is from us. And as a result, basically like you know which string is going through which galaxy.
Okay.
Right. And we can do like once we do this cross correlation, we know like there are a few spots in the sky where like this crossing could be happening, and we just point our detector at it and see look for it.
So I mean, does this not depend? I would have thought this depends a lot on the signal characteristics, right? So I mean, if the, you know, if the, for example, if these were blobs that were blobs of charge that were colliding, and they were the size of order, the separation between the galaxies, you know, and they sort of smoothly turned on and off, are these really, I mean, maybe I missed something, but are these really dramatically different from just, you know, stuff you see, like you just see galaxies and they're not exactly constant brightness because stuff moves around and because you have foregrounds? What is it that makes this signal stand out? Can you say something about what makes the signal stand out from just ordinary garbage?
So the collision is a point source, right?
How point-like is it?
It's as point as basically like how, like what's the charge density around the string is located.
Yeah, but I mean, it's not it's not set, for example, by the separation. These two galaxies that are sourcing this, this excitation, it's not of order the size of the separation between those two galaxies, for example?
No, like because like the rest of it hasn't collided yet. The colliding is really happening at a point.
So each of these things is of order the size of the galaxy, and by the time it collides, it doesn't spread out significantly. It doesn't spread to be sort of order this initial separation.
No, we don't think like it will spread like this. Like it will like spread like in the other directions. So you will create something like a fireball, like from these charge, like you will have like a positive charge particles and negative charge particles, right? In the cloud, which collide with one another, so they annihilate.
No, I mean the lump that's moving along the string. It's sourced by these two galaxies.
Yeah.
I understand that these galaxies look like pretty point-like, right? Because we're, you know, galaxy separation is large compared to the galaxy size. And so they're in that sense, at least they're point-like. But now this excitation starts moving along the string. It doesn't spread as it moves along the string. Causality would allow it to spread of order the initial separation. If it spread as much as it possibly could,
so
let me, it would spread, right? And that wouldn't look very point-like.
Sorry, like let me stop sharing like here, and I can draw you like what we actually see. Oh, actually, like I cannot like draw with my iPad.
You can wave your hands.
No. Like I mean, like I do not have like host. Like my pad is not host,
John,
so I cannot draw.
Can you give him the capability to?
Yeah, I can draw it.
Maybe we can defer that question for a second. You know, maybe this is getting a little bit longer discussion. Let me give somebody else a chance to ask a question, and let's come back to that in a little bit, okay?
Yeah,
because
sure.
I've already asked a lot of questions, so let's give somebody else a chance.
I have a very basic question for the screen production. So how large can Xi be in the perturbative controlled region? Because somehow you lost perturbativity, right?
For Xi?
Yeah.
No, I think like you can, like it can be like Xi is a number which is like some integer times a log, whereas the log is order 100 times another integer.
So basically, you're saying Xi can be like larger than 10 to the 4. Still, you can.
Yeah, it's all perturbative. Yes.
It's still perturbative. Okay.
Yeah. There's no like it's not a coupling, right?
Sure. But the string production is a proportional to some coupling, though. I believe.
Yeah, so yeah. One thing like you can think about is actually like as the universe is expanding, right? Like you keep like this scaling solution, and that is actually diluting as more than the naive what's the naive redshift will tell you. Like if you do the naive redshift, like C will like increase like crazy, but like because of the string interactions, C is kept roughly as a constant.
Okay, sure.
So there's always like a lot of string, like initially like you will have like a lot of string, and like then like they reside into this scaling regime, and the fact that like the scaling regime is an attractive solution means like the initial condition doesn't matter. So there's no dependence on like how you produce these strings.
Can I think of that as very, very roughly? Can I think of that as, you know, strings will annihilate whenever they find each other, but and so they do that until there's only very, very roughly order 1 per Hubble left, and then they
Yes.
can't find each other anymore.
Exactly.
So that's why Xi is not some astronomically exponentially large number. It's order 1 to thousands or something like that.
Yeah.
Is that intuition roughly correct?
Yes.
Okay. Okay,
Yeah.
sure.
Other questions? Maybe I can ask my question again then. I mean, did it, I don't know if did it make sense? I'm imagining there's a string like this, and I mean, a galaxy creates an excitation here and here, and then these excitations start moving towards each other on the string at the speed of light. But
Yeah.
if they're also spreading at the speed of light, right?
Yeah.
Which
Yeah.
kind of your picture of the dissipation sort of made me think that maybe they are. If they only make it around order 1 times, it sounds like you're telling me they're spreading, also sort of spreading at the speed of light, but then they
Yeah.
wouldn't be a very point-like thing. I'm wondering, is that correct?
Oh,
or
why? Like,
take
because
that into account?
the spreading is all in like 1 + 1d, right? So if you have 2 charge
That's
over
right, it's
densities, which
spreading
are all like,
along the string, so it would still be point-like, of course. So is that what you're assuming? You're assuming it could be spread all over the string this way, but of course it's on the string, so it's a
yeah,
line.
it's always on the string.
So so it is spread out, but it's a line. It's like the string is flashing.
Yeah.
The string is flashing.
That's right.
That's the picture.
Yeah.
Okay,
Like
sorry, I
the
didn't
zero
get
mode
that.
is not moving in the perpendicular directions. They are confined on it.
No. Okay, I understood that. Okay, so
Yeah.
really, but it's not like, but then it's not really point-like. It's like line-like, or it's a
No,
little
but like
segment line.
sorry, yeah, it will be better like if I can draw, but I think John is not around.
I'm telling you, you're gonna have to wave your hand.
You cannot just draw and share with your MPad.
Well, I think John has to let him share. But
I need to be
shared your iPad, didn't you share? Isn't that what you used to share your slides?
No, I used computer to share my slides.
Okay,
Sorry.
yeah. All right.
Yeah, that's you want the other account to be co-host, right?
Yeah. Can I make myself co-host?
John?
Yeah, I think he's
probably muting us as well. So
yeah.
Okay, it's okay.
Okay, so but then like let's see. I have a blackboard.
Oh, great! Yeah. Blackboard. I remember those.
Okay. So can you see like
Yeah, we can see it. If you do it on the light part, the part where the sun is shining on it.
Yeah. So here.
Yeah.
Yeah. So what you have is like you have a string, right? And you have a charge over density. Let's say like you start here, right?
Right.
Let me draw them closer actually. And then like as they propagate, what happens is like this guy is going to propagate this way, and the other guy is going to also propagate this way, and they spread out, right?
Right.
So here, like let's say like this is plus charge and this is negative charge.
Yeah, I forgot that they even go the same way. So they don't actually collide. They just catch each other or something.
Yeah, they catch each other.
Okay, yeah, all right.
So I have positive charge and negative charge, and the catching up is only happening here, right?
Yeah.
And that's where like you look.
Right. Okay.
You're not going to have like signal here or here.
Yeah. No, I get, but so it is sort of spread out over the string, right? It's kind of spread, and then it keeps spreading. So it's kind of spread out on the string, but I understand. But of course, it's on the string. That's the
So the luminosity as a function of like a string length, okay? Let's say collision happened here, is going to be some function like this. Okay. So even if it is just spreading, it has some like luminosity.
Right, sure.
Because the spreading itself gives you dissipation. So there is some luminosity here as well. But like you will see like a peak is something you can target, which is coming from this collision. And you try to see like if there is a line-like feature around it, which is where like the string is.
So you can literally resolve these lines, right? Because because you can, if you can resolve these experiments are able to resolve the fact that you see literally a line excitation.
You can like see like all the spot, right? And you can like see like if they align.
Okay, yeah, you would see a bunch of, okay.
Yeah.
Okay, cool. Yeah.
The angular resolution like for like these distances, it depends on the experiment, but like I think like for like each of these collisions, the total region where like the energy is emitted is like maybe like a 10 to 20 pixels.
Okay.
Yeah, so there will be a bright spot and then like a slow decrease.
Right.
Like I didn't confess, but like we cannot compute like exactly how that looks like.
So you say on the string there will be many creations on the string.
Yeah. So the light is going to come from a region on the string, which is a line-like feature, but like there, because the collision is a point, so you target the point as a trigger, and then like you look for like if there is a tail.
So how bright is this compared to, let's say, the galaxies that are sourcing it?
Yeah. So like as I was saying, right? So let's say like you have like two galaxies which are here. When this collide is not inside the galaxy.
No, I understand, but I'm just wondering to get a measure of how bright it is. Like, is it? I mean, I guess I'm sure you thought about backgrounds, right? So
Yeah.
what? Let me ask like this: what is the biggest background to this?
So for a dedicated search, like it's just the background light. You are like the extragalactic background, like a radio emission. And for like blind search, then like you need to like say like, oh, this is a galaxy or this is not a galaxy. So that is much harder.
Okay.
Yeah. So blind search may like you need to like target to like a few points, which are like consistently bright, which is like a straight line, which is much harder. Like I don't think that's possible actually. But which is why like we probably need the dedicated search to be like to see these things.
Cool. Other questions? Any other questions? Well, let's thank Junwu again.
Thank you.
All right. John, can you turn off the recording? John.